Welcome everyone to the APS Journal Club, which is organized by Physical Review Letters. Good afternoon, good evening, and good morning, depending on where you are watching us from. So today's Journal Club is also made to celebrate, in part, International Year of Quantum and the achievement in quantum science that has been happening over the last 100 years, and especially in the last 2 or 3 decades. Today's talk will be about superconducting quantum computing with chips that are beyond 100 qubits in size. Presenter would be Xiaobo Zhu from the University of Science and Technology of China. It was published in Physical Review Letters earlier this year. And with that in mind, let me say a couple of words about the Physical Review Letters. Physical Review Letters is a journal that is now over 60 years old. It is a most cited journal in multidisciplinary physics. It is a most influential journal in multidisciplinary physics by any measure that is. And in recent years, it has been publishing papers for 13 Nobel Prizes, for 13 consecutive years of Nobel Prizes. So we are very happy that we were able to publish the work of Xiaobo and the group at the University of Science and Technology in Hefei, because this is one of the breakthrough works and the kind of work that we really like to see published. Now, before we continue, let me just say a few words about the Journal Club and the way we do it. Please, all of the participants except the speaker, mute your audio so that there are no other sounds coming out. We are asking you to hold your questions until after the talk is over. While the talk is going on, you can write your questions in the chat box, but we are going to ask them once the talk is over. You can also use the reaction, so you can raise your hands, and after the talk is over, you can turn your camera on, your microphone on, and you can ask your question in person. So with that in mind, I hope you enjoy the talk. I will stop sharing and I will ask Xiaobo if you can start sharing your presentation, and you start your presentation.
Okay. Should I start?
Yes, please.
Okay. See the screen? Okay, can you see the screen? Hello?
Yes, it is working well.
Okay, no problem. So let me start. So today, I'm very glad to show our recent result about superconducting quantum computing. The scaling, we have scaling over than 100 qubit. I'm Xiaobo from USTC, China. And in the very beginning, I just show some basic things about the superconducting qubit. You will see, in fact, the superconducting quantum computing is utilize the so-called superconducting circuit to form as superconducting processor. In the processor, in fact, it contains inductor, capacitor, and Josephson junction. It's just if we can lower down the temperature and also lower down the noise level, so it can be show a macroscopic quantum effect, and finally it can form the quantum qubit. And since this kind of processor can be operate like the traditional processor, it just use the pulse, the electronic pulse, to control it and to read out and to operate it. So it's convenient to scaling up, and that means we can easily integrate a lot of qubit. But since it's a macroscopic quantum effect, So it can be easily affected by a lot of noise, like single electronic noise or single quantum particle noise. That means it's very weak. The system is very weak, and it's very important to improve the quality of the qubit systems, the superconducting systems. And relatively, the quantity is easy because we can just use the traditional semiconductor technology to integrate a lot of qubit on one chip, and finally we can have a lot of qubit on one chip. But the quality, that means how good we can control our qubit is much more challenging. So in fact, I think this work is just how can we improve the quality of the qubit very much, and finally we can go to so-called quantum advantage and show in the RCS problems we can have a very good performance. So in fact, nowadays the superconducting from since the first I think first result in 1999 just show a single qubit. Nowadays it improved very quickly, but we still has a very long distance to go to the so-called universal quantum computing. Here we see, in fact, at least we need to consider two aspects of the systems. One is the number of the qubit. Another important thing is the error rate of the qubit. You will see, even we have a lot of qubit, if our error rate is high, that means it's easily to simulate by the classical computers. So can we running a problem that's beyond the ability of the classic computer? It's the first our first target. That means the superconducting quantum computing advantage, or we call it supremacy. In fact, nowadays in the superconducting systems, there has two machines. One is Zuchongzhi and another one is Sigma. And the newest generation of the Google's video also shows that ability. We can run a problem that is faster than the classic computer. So we call it quantum supremacy or quantum advantage. That means we for the first time the computational ability is stronger than the classic computer. But you will see in this region how many qubits and what's the error rate we are. It's just like several point 0.3 or 0.4%, and also tens to 100 qubit. That's we are here. And so in the future, it's extremely difficult to go to the really so-called universal photon quantum computing, because you will see that may need error rate lower down than 10 to minus 12. But for the real physical systems, it's extremely difficult to improve the fidelity. That means we lower down the error rate. So we believe maybe in the longer term, what we can do is just integrate more and more qubit, and maybe we can gradually improve the error rate lower than 1,000. But that's it. So that means if we look at this, we will think we can never go to the universal quantum computing. But luckily, we have so-called error correction. So nowadays, the theory of the error correction improved very much, and the threshold of the error correction nowadays is just maybe 0.6%. So that means if we can have an error rate lower than go to the 1,000, we have the chance to form the very low error rate logical qubit. And if we can integrate such kind of logical qubit, we can finally go to the universal quantum computing. But the error correction, in fact, is much more difficult because that's also needs a very good quality of the whole systems. I will show a little bit details of this kind of issues later. So what we developed the quantum process we named Zuchongzhi, and in this device we in fact we integrate 105 transmor qubit and also 182 tunable couplers. in fact, the tuning couplers, we need a very similar resource to control it like a traditional qubit. That means, in fact, we need at least 300 channels to control all the systems. And in fact, the design of this kind of process also match the surface code. So as I said, it's important to realize error correction. Otherwise, we cannot really go to the universal quantum computing. And also in this kind of samples, we improved our coherence properties very much. We optimize quite a lot of circuit parameters and electric field distribution. And also, we update the fabrication processes and the materials, so we can have a average T1 time of over 70 microsecond. And also, we spend a lot of time to improve the readout effect. So we implemented a bandpass filter that can help us to read out the qubit quickly, but also not affect the coherence property of the qubit itself. And also we just tuning the carbon strength and bandwidth very carefully in order to keep a very efficient readout, as well we can keep the very good coherence of our qubit. In fact, nowadays the so-called quantum advantage or quantum supremacy problems, both are sampling problems. In fact, the first conception was just on a linear optical systems. It's just boson sampling in the linear optical systems, and also we can prove the classical running time can be proportional to the exponential increased. So that means the class computer, if we can have, for example, relatively larger scale of the systems, the class computer cannot easily to simulate it. So later people found in the superconducting system, we can run a so-called random circuit sampling. This is also a type of sampling. It's just running randomly, quite a few layers of single-bit gate and two-qubit gate, and finally to sampling the problem and to see if it satisfies some Thomas distributions, and to see we can sampling succeed or not. So we can also estimate the complexity of the calculation. Such kind of problems is also is not easy to simulate by the classic computer. So that's suitable for the gate-based quantum computing systems. Since quantum computing, we always believe there's some ability that's much stronger than the classic computer in theory, but there's no experiment to prove that. So people are at the first stage. People are struggle to find out, can we show such kind of interesting things in experiment? I think the first conception was proposed in 2012, and after that, I think the first result was appeared by Google on SIGMO superconducting quantum computing, and in 2019, and after that, in 2020, in USTC, we show the quantum advantage in the linear optic systems, and after this, our Zuchongzhi 2 USTC in 2021, we show the quantum advantage in the superconducting systems, and also you will see the linear optic system improved from Zhejiang to should not do, and to Zhujiang-3. And also we see our the superconducting regions signal improve very much, and Zuchongzhi 3 also show the strongest quantum advantage until now. And today we just introduced the Zuchongzhi 3 here, and you will see the RCS in fact benchmarking over all the quantum processors performance, including the gate, the readout fidelity, the stability, connectivity, and the sampling speed. So that's I think is very good benchmarking of the whole systems to go to next step. So I will show a little bit details of Zuchongzhi 3. In fact, we use quite a lot of calibration technicals. We can improve for example, the XY crosstalk calculation. We can improve our single bit gate less than 1,000, and also we can dynamical decoupling dynamical coupling off the corrections, and we can improve our two-qubit gates, and also we can use the active reset to improve our readout fidelities. And finally, in our Zuchongzhi 3, we have 105 qubit, and we have single bit gate like 0.1% fidelity error rate, and two qubit gate 0.38%, and readout error with 0.82%, and the T1 improved to almost double, more than double the Zuchongzhi 2. So that means we can have a much more stronger performance. And finally, we running 83 qubit with 32 cycle random circle samplings. And we can estimate the running time on the for example, the most powerful supercomputers, and we can estimate our 83 32 layer RCS programs. If we running on the frontier, it maybe need 10 to 9 years to simulate such kind of programs. So that's the conclusion. We in fact improve the quantum processor Zuchongzhi 3, and it's in fact with very good correlation time and readout efficiency, and also our single bit gate and two qubit gate. I need to emphasize in the future what we are doing now is so-called surface code error correction. We see. In fact, this kind of structure and this kind of gate operations is quite similar to the surface code. I think last year, at the end of last year, Google already showing a distance 7 surface code, and very impressively, they also show when the code distance become larger, the error rate becomes smaller. That means we have the chance in the future we can really achieve the so-called fault tolerance quantum computing. That means we can have chance for error, a very extremely low error qubit. So in fact, in this Zuchongzhi 3, we perform a similar experiment to see in this kind of processor we can really shows very good error correction properties, and to show to prove in the future if we can have a chance to go to the universal quantum computing. And that's all. Thank you.
Thank you very much for a very nice talk. I have quite a few questions to follow up, but before that, does anybody else have any questions for Xiaobo?
Okay.
Robert?
Well, I have a couple, but I'll ask one. Could you talk about why you end up using 83 instead of the 105?
Because at that version, in fact, we have a 1 or 2 defect, and because of that kind of defect, you cannot connect more qubit. So that means the layer we estimate the complexity of this whole systems. So if we running more qubit because the connection is not good, so in fact the complexity become lower. But now we have improved our recipe of the fabrication. We have better samples, so I think we can running more qubit on such kind of processors. Yeah.
All right.
Faisal?
Should I ask another question, or you want to go ahead?
To be
Go
honest,
ahead. I'll ask. I'll ask later. Go ahead.
Faisal?
Yeah, that was a very interesting presentation. Thank you. I noticed that you increased the coherence time from 30 microsecond to almost 72 microsecond by optimization and fabrication improvement. So what is the theoretical upper bound estimation of the T1 that is your goal, for example, to improve your coherence time?
Okay, that's in fact a very good question. In fact, so currently I think one of the bottom problem is the coherence time, especially the T1 is the limitation for the whole systems because our gate duration time is like 30 to 40 nanosecond. That means the coherence error is still one of the main challenge of systems. But luckily, we see quite a lot of result that can improve the coherence time of the qubit to like several hundred or even a millisecond T1. Our estimation is if we can go to like several hundred microsecond, that's enough for the qubit system because you can estimate the decoherence error then. But from single qubit to integrate so many qubits into one processor, the T1 coherence properties is totally different because the electronic environment is totally different. You can just play one qubit in a very clean environment and have a very good T1. But if you really want to improve so complicated processor T1 properties, you need to consider a lot of properties. For example, when we consider to improve our readout effection, we need a very strong coupling between the qubit and the readout circuit because we want to exchange the energy between the readout circuit and the qubit very much. Then we can quickly read out the signal. But if you have another system coupling to the qubit itself, the T1 become worse. So we have to balance this kind of issues. So as I introduced, we just introduced some bandpass filter to just use the different bandpass to prevent such kind of bad things happen. So we hope in the future we can go to like 200 microsecond. Then that means the decoherence was not the key issues. So that's the T1.
Any other questions, Robert? You want to ask your follow-up?
Well, he almost answered it. I was going to ask.
All right.
Yeah, I was basically going to ask, how do you balance the fact you have to couple to do the readout, and that's going to hurt your decoherence time. So how do you make that? How do you make that optimization decision?
In fact, the first thing is we want to use bandpass filter, like using the readout worked, for example, high frequency like 7 gigahertz or 6 to 7 gigahertz, and use our qubit worked on the 5 gigahertz. So that means we can filter the noise. This is one of the important things. And also, we very carefully calculate, simulate, and test the coupling strength to choose one just we can the readout speed is acceptable, and also the decoherence is also acceptable. So that's what we're doing. So, but in the future, because we want to multiply readout the qubit now we use the 1 to 6, 1 to 7 multiply channel readout. But in the future, if we scaling up the system very much, so we need much more bandwidth to read out the qubit. Then maybe it's difficult to balance this kind of things more and more. So still we need to try to solve this kind of problems,
So I have one very general, big picture question. You have shown on your timeline of the development of a quantum computing architecture, you show your processor with 105 physical qubits there, but you've shown the earlier processor from your institute as well, which is based on the linear optics and the photonics simulation. So can you compare these two architectures, and can you let us know which one and why do you find more perspective for future scaling, upscaling of the systems?
So you've been compared the two technical lines. So I'm just familiar with the superconducting. Maybe Chaoyang is suitable guys to Chaoyang.
Excellent.
Can you talk a little bit about linear optics things?
Hello.
Hello. Hi.
Yeah, talk a little bit about linear.
Can you say your question again?
Yeah,
I just use a VPN, so there's a connection. Sorry.
Yeah, I'm just asking if you can compare the two physical architectures, the superconducting architecture with the photonic architecture. How do you foresee further development, scaling up of those? Where are they going, and which one would you think will carry on further?
Can you hear me now?
Yes, we can hear you.
Okay, yes. So currently, actually, we are pushing different platforms based on different physical systems. Actually, in China, with Xiaobo, and also with a few other colleagues, we are not only doing superconducting qubits, but also based on photons and neutral atom arrays in optical tweezers. So I myself, I was pushing the photon-based approach. In the past, we have demonstrated quantum computational advantage with photons and linear optics. Actually, we are just finishing our newest experiment of Gaussian boson sampling with up to 3,050 photons out of more than 8,000 modes, and therefore we demonstrate a very robust quantum computational advantage. But in the future, we would like to push for another routine, which will overcome the 30 years old challenge that single photons do not directly interact. Because it's a common challenge in the field for the past, I think, 30, 40 years that the single photon nonlinearity is too weak for them to have direct interaction. So what we would like to do is to engineer the direct interaction so that two single photons can have a deterministic and high fidelity C0 gate. Therefore, we would like to transform the field of linear optics, linear optical quantum computation into nonlinear optical quantum computation. If we succeed in this direction, then I think photonics, which was usually, sometimes some people call it ugly duckling in the field of quantum computing, and many people don't believe it will succeed. I think the ugly duckling could become one of the most competing platforms for quantum computing because of the advantage of the, the photonic will not need any cryogenic cooling. but we can do all the quantum computing experiments in room temperature and scale to like millions of qubits, and with additional advantage of very convenient interconnection between the distant optical quantum computers. So yeah, so that's our main goal in the next like 3 to 5 years. We are confident that we can have a deterministic synergate in the next 3 to 5 years. And I think the field will be very happy to see finally, two single photons can talk to each other every time. And yeah. And in terms of the other platform I just have mentioned, neutral atom arrays in optical tweezers, actually we also have started a few years ago. And I think this week, maybe today or tomorrow, we will have a paper published in Physical Review Letters. We actually use AI to rearrange the atomic arrays to a scale of 2024. So why this number? This is like the last year, because we have array of a square of 45 times 45. So that the result is 2025, and we have one defect we have only one defect in this two-dimensional array. So we end up with 2024 atom arrays. It's the most intriguing feature of our atom as Robert.
No, I was just going to say
yeah.
That was one result that we. All right, never mind. It's not important. Never mind.
Yeah. I want to add that the most interesting feature of our new atomic rearrangement algorithm, atomic size. No matter you want to rearrange like 10 atoms, 100 atoms, 500 atoms, or 10,000, or even 1 million atoms, the time overhead is constant as a function of the atomic array scale. So actually, I think many groups are now start to use our new AI-based algorithm. So it's a very exciting approach. And we have seen many exciting results in our community from Michel Lukin's group and Tony Bloway's group and many others. So yeah, and another paper actually we also submit to Physical Review Letters. I'm not sure if I can say it secretly. Is we have performed a century-old thought experiment originally proposed by Einstein and Bohr, actually in the 5th Soviet conference, that when Einstein hopes to challenge Bohr's complementary principle and proposed a genius recoil slit experiment, and we find that the single atom in optical tweezer cooled to 3-dimensional ground state is ideal candidate to faithfully realize this century-old thought experiment. So we use a single atom in ground state as a quantum limited beam splitter, and it can actually sense the momentum kick of a single photon. And therefore, we reproduce Einstein's thought experiment. We can see a gradual change as we use the laser to tune the momentum wave function of the single atoms. Yeah, so yeah, I think this is also a very exciting approach. I think in the near term, people will very quickly be able to control up to tens of thousands atomic qubits. And also, I think recently in 2 months ago, I think Michel Lukin's group, they have 2 new very exciting new papers on arXiv. One is to demonstrate the quantum error correction above the threshold, and demonstrate the break-even point, and also demonstrate the continuous operation of atomic quantum computers. So yeah, I think all these approaches, they have their own advantages and disadvantages, and they will push forward, and we will see a very exciting development. Okay.
Excellent, thank you. I have just one more question. One thing caught my attention in your answer when you mentioned nonlinear interactions between the photons and deterministic CNOT gates. What kind of nonlinearity are you using, and what is the physical system that exhibits this nonlinearity for a deterministic quantum gates?
And remember, you're being recorded.
Yes. Hello.
So he may know.
So I now moving closer to my to my audio because I couldn't hear clearly your question. Can you say again?
Yes,
yeah.
Yes. Regarding the deterministic quantum gates, the CNOT gates that you mentioned, based on nonlinear optical interactions, what kind of nonlinearity are you envisaging, and what kind of physical system will exhibit this nonlinearity?
Okay, yeah, thanks. Okay, actually, we are trying two different approaches to get this photon nonlinearity. One is based on quantum dot spin confined in a strong coupling microcavity. Actually, it's open cavity, open microcavity, which we have recently used it to demonstrate the brightest single photon source above the photon loss threshold for linear optical quantum computing. We have 71% end-to-end efficiency, meaning under pump of 80 megahertz laser pulse, eventually we will detect more than 55 million single photon counts per second. So so if I recall my when I first entered the laboratories, also during my PhD in Cambridge, during my PhD in Cambridge, you only saw a few hundred counts, but now we have 55 million counts. So really, so the field is moving forward. So not only is quantum dot spin in strong coupling cavity can help us to generate the pure and indistinguishable single photons, but also it can mediate the deterministic interaction between two single photons. So this is one system. Another system is based on spontaneous parametric dawn conversion in ring cavities. So what we want to do is to have the Chi2 nonlinear interaction between two photons, and we are now engineering a high Q cavity and with deterministic with strong nonlinear interaction, so that we can isolate. Our aim is to increase the interaction and decrease the loss, so that we can reach a strong coupling level that we can isolate a two-level system. Actually, it is very similar to the superconducting qubits. So the nonlinearity will cause unharmonicity strong enough to isolate a two-photon, a two-level system. And we put forward our own theoretical proposal on how to use this ring cavity, actually coupled ring cavity, to induce a two-photon phase gate and to implement the two-photon CNOT gate. So to answer your question, in short, we are implementing, one is using quantum dot spin in strong coupled cavities, Another is to have strong coupled nonlinear optical materials.
Excellent, thank you. Now, Xiaobo, what can you tell us about your vision for superconducting quantum computing?
Yeah, in fact, of course, surely we just focused on scaling up more and more qubit, and as well we need to improve the quality of the qubit. And I think the key issue for the next generation is just one aspect is of course the processor itself, but gradually we found the electronic control become more and more challenging. You see, because we need very good control for each channel of each qubit, like at least 1,000 precisions. So you will see nowadays we still only using one set of electronic device to control one channel. So that means each qubit we need at least connect one cable to one system. That means if we have, for example, nowadays we have several hundred qubit, maybe in the future, several thousand or tens of thousands or million qubit. That's undoable. So the key issue is how can we make our electronic device become more compact and like use the traditional semiconductor technicals finally become a control chip. Maybe we call it cryo chips, or you see, in fact, this kind of field is also attract a lot of attentions. If you look at the IEEE conference, they are more emphasizing this kind of cryo small systems. And also another important issues we can consider is the so-called SFQ system, single flash quantum system. That's a technical based on the superconductor material itself. It also can realize very similar function like the traditional semiconductor electron devices. And maybe this kind of things has been developed maybe in last century, like 1980s or 1970s. It's attracted a lot of attention, but finally, because it needs low temperature, it's failed competed to the semiconductor ways. But maybe 2015 also IBM just restart 3C project just to make a superconductor computing, just use this kind of SFQ circuit. And we believe this is maybe one of the most promising way to control the superconducting quantum computing itself, although there's a lot of challenge. So we make a lot of effort to see if we can have a chance to use this kind of superconducting electron devices to control the qubit in situ. And finally, can we integrate the control system and the quantum process together? That's maybe the real way we can scale up to see a good superconducting quantum computing. Although there's a lot of challenge because the SFQ system, in fact, not developed as well as the CMOS systems. So I think at least this kind of two-way will compete for a long time. I also see the cryo CMOS systems shows a lot of result, but they may. Most of this kind of paper they publish on the IEEE or the CMOS conference, not in the PRL or the physics journals. So I think SFQ have shown quite a few results. Recently we submitted a paper, and unfortunately maybe one of the referees not happy with this result. They said still it's not enough impressive. So I'm just think this is the way how we can in the future improve this kind of things. So this is the bigger issues in the future. I think in one word, that's into how to control such kind of a big system. That's one of the important things. And also, since the qubit integrate more and more, and the energy consumption is a big challenge because what we work in is very extremely low temperature, like 20 millikelvin. That means we cannot have a very good cooling power at that temperatures, and we almost approach the quantum limitations if we just integrate more and more qubit. So that means we need to develop the more and more powerful dilution systems to have more cooling power. So if this both are working very well, technically, of course, it's the error correction. If we can really have a very good logic qubit with extremely low error rate, and also if even we have very good logical qubit in the future, we still maybe have a lot of problem like how we integrate more and more logic qubit, and finally to running very good algorithm. Nowadays, quite a few people are emphasizing, can we have a chance in such kind of NISQ stage? That means even every qubit has noise. It's noisy. We can only run a very limited quantum gate. Can we show some useful problem we can solve it by the quantum computing, even we have, for example, 1,000 error rate? But I'm not very sure because the algorithm itself is difficult. The theoretical guys told us, how can you imagine just running a program and it's complicated than the class computer and with only very limited quantum gate? Can you design such kind of algorithms? So we are, of course, for the hardware, we will improve this kind of things gradually, year by year. For example, maybe next year I will give a talk over 300 qubit with the still very low error rate. But for the algorithm itself, there's very challenging. How can we solve a problem with very limited quantum gate and with very limited qubit? So I'm not, in fact, for the NISQ, I think maybe the quantum simulation has chance to show some good result better than the class computer. But for the gate model, I'm not sure if we can really run some problem in the NISQ stage. So this is my feeling. Anyway, I hope there's some output in the NISQ stage because that means it can attract more and more attentions. Anyway, if it has real applications, it's very good for the quantum computing. Otherwise, we have to wait in the fault tolerant quantum computing. I hope it will not come very late, but at least I think it takes more than 10 years. So that's my feeling. Okay.
Okay, thank you. Robert, do you have a question?
I actually have a couple. So is there any possibility of having, sort of long distance gates, the sort of the way that, like Misha Lukin can sort of move qubits around all over the place, or is the architecture just really confining you to that? And then the second question is, what is the behavior of the coherence time versus the temperature? I mean, does it level off as you go below, or is it continuously longer as you get lower temperature?
So, sorry, the first question is
maybe the gates. So your gates are you're fixed there. But can you build it so that it has longer distance gates, or how?
Oh, that's really an interesting question. In fact, so the connection, for the superconducting qubit is not as good as neutral atoms or some other systems because we are just fabricate on a chip. It's just a near neighborhood couplings. So that's why we choose the surface code. In fact, okay, not the LTPC code. Okay. But in fact, we have some other way. For example, we can use 3D wiring technologies. So just we can have better connections. But the key issue is how can we realize like 1 to 6 connections? That's in fact while we keeping very high fidelity gate operations. That's very challenging. You see in the IBM processor in the past, their connection is 1 to 2 or 1 to 3. So that means they can not easily go to the source code. For the source code, typically we need 1 to 4 connections. So we have some project where we are really put forward this kind of things. We can see if we can go to 1 to 6 connections. If we can go to 1 to 6 connections, we can have a chance to 3D structures. I think the 3D structures we are not saying good enough, but at least it's much better than the 1 to 2-dimensional connections. And at that time, I think, in fact, there's quite a theoretical work point out that in that structures, we can use much less qubit to realize very good error correction code and with much higher efficiency. Maybe not as high as the full connection result, but at least it can save a lot of qubit resource. So I believe it will follow the semiconductor way. It's maybe 2D or in the future 3D, but we will not go to a full connections. This is for superconducting way because that's very strong challenge for the technical issues. So that's the best way, I think, in the superconducting way. And maybe we can introduce some resonator to connect remote qubit, but I don't think this is can easily scale up to a large scale qubit systems. So this is for the first question. Second is second one is T1 or?
How does T1 depend on temperature?
Oh, yeah, that's a very interesting question. In fact, the T1, even we warm up the system to about 100 or 200 millikelvin, the T1 didn't drop very much. But the key issue is the thermal activation of the qubit become worse. So that means the initialized error become larger. So in the real computation, besides we develop some unique like reset technicals, we can reset the initialized error. So otherwise, we would like to keep the initialized error as small as possible. So that's why we choose the temperature worked at 20 millikelvin. But if we can reset the qubit very well, I think in the future, the qubit itself worked at least at, for example, 100 millikelvin or 200 millikelvin is doable. That's my feeling. Yeah.
Is there any other question? If not, then I believe we are nearing the end of the Journal Club. And I would like to thank you all for participating in it. Xiaobo, thank you very much for a very nice talk. And everyone else, thank you for a very nice discussion that we've had afterwards. Robert, would you like to say a word at the end?
Oh, yes. Well, I just wanted to thank you, Xiaobo, for taking the time out of your day to put together a talk and to speak. And I'm sure there'll be, there were quite a few people who signed up for this who will see it in the recording. Again, the time is late for a lot of people, so it's easier, particularly if they're in Europe, to see this. So thank you very much, and thank you for submitting your great work to us. We look forward to the next generation of devices, both kinds of devices, so that's it. So thank you very much, and thank you for the people that are listening now, and we'll listen to the recording.
Okay, thank you very much. Now the Journal Club, PRL Journal Club, runs typically once a month. We try to cover different areas of physics that PRL publishes, but this being an international year of quantum, we are foreseeing about a couple of more quantum talks before the end of the year. So watch this space. We are going to keep you informed about the future talks. Thank you very much.
Thank you.
Good night and good day to wherever you are.